This video covers the last functional form we are looking at in quantitative methods, exponential equations. And so what we're going to do is look at how we can use them to explain growth, decay, and interest rate problems. I'm sure all of us at some point in time have used a trend line in Excel. And so we graph our data, we click on the line, and then we say format trend line. And I have to decide, well, which trend line do I want? And maybe what we've done in the past is just sort of clicked around till we found the one that fits the best. And so a lot of times what people do is select polynomial, because the more sort of numbers I click on the order, a lot of times the better fitting my data may be. But if I have real GDP over time, and I think that a polynomial that raises to the fifth power is the thing that explains it, and somebody asks, well, what does that mean? I don't have an economic explanation. And so what we're going to do is spend a lot of time looking at exponential equations, because they have some unique and interesting properties that work well with things like real GDP growth. So the takeaways for this topic are the following. One has to do with a lot of the language. And I think the language gets confusing for people. We will be using this thing called logs, and specifically a natural log. And a natural log isn't something that is organic. It is non-GMO or something that I would buy at Whole Foods. All it means is it's the log, just like any other one, but of a very specific number called E. And E is just a number like 10. It's just less than 10. And the other thing is, usually economists, if they say it's an exponential function, they mean of a very specific type, where y is equal to E, that E returns again, raised to the RT. And we'll talk about that in more detail. So here is my exponential function. And what makes this exponential is look at the position of where x is. X is now in the exponent. So anything that has a variable in the exponent is an exponential function. Most of the ones we will look at look something like this, although I want to take the b and get rid of it. But before I do that, just to remind you that a and b are the constants in this, x and y are my variables. And so if I substitute my b and stick in an e, I'm getting closer to things that we'll get that we'll use a lot this class. I want to now get rid of my x, because actually what economists look at would be things like population growth, interest compounding. And so it might look something like this. Y is equal to a e to the RT. So let's look at this in a little more detail. A is my starting value. So if I were looking at population, either growth or decay, that is at my point of the beginning of my analysis, that's the starting value for the population. Y is the ending value. That I may not know what that is. I may want to solve for, in 10 years, what is the population? Or maybe I want to ask something else and I have the ending value, but that's the ending value at a period of time. R is my growth rate or my interest rate or my rate of decay. It's the rate of change. And T is the number of periods I'm looking at. So let's look at an example. Here's a car. And let's say that this car, when you buy it new, before you roll it off the lot, is worth $100,000. It depreciates each year by, let's say, 5%. And you wonder, at what point in time will this car that I bought for $100,000 equal only 50? I can use an exponential equation to represent what's going on. So my starting value is 100,000. My ending value is 50. And my rate of decay is 5%. So if you notice in the exponent, it says minus 0.05. And the minus sign is needed to show that this is a decay function, that the value is approaching 0 over time. And then there's this t. And what I want to know is, I want to know what is that value for t, but my variable's in the exponent. What am I going to do? I don't know how to solve that. I need some help. And where do I get this help? From logs. So let's take some time to review what exactly are logs. Logs help you answer the following question. To what power would I need to raise a base to yield a certain number? So for example, if I have 10 squared is equal to 100, something we all know, what the log would say is, well, what do I have to raise 10 to if I want to get the number 100? And the answer is 2. And so the way I would write that is log base 10 of 100 is 2. Another example. 2 raised to the 4th power is 16. And so what the log question is, what do I need to raise my base 2 to get the number 16? And the answer is 4, where 2 is the base. What we use a lot is e, and e is, again, just a number, and you can see it on your calculator. E to the 6th power is 403.4. And so what the log base e says is, what do I have to raise e to get 403.4? The answer is 6. And you'll notice that third line, looks a little different. And one of the things that we do is if a logarithm is of base e, we call it a natural log. And so we use ln, and we don't write the e. So it says a natural log of 403.4 is 6. It answers the question, what do I have to raise e to get that number 403.6, or 403.4? So there's some rules for logs that I think will be useful for you to remember. The first, any number raised to the 0 power is 1. So e to the 0 is 1, a million to the 0 is 1, and so on. So based on that, the natural log of 1 is 0. E raised to the 1st power of 1 is equal to e just like anything. So that tells me that the natural log of e is 1. And those two items, natural log of 1 is equal to 0, the natural log of e is equal to 1, will be useful in solving some problems. But perhaps the most useful is the thing that's written in red. What is the natural log of e raised to the n power? From the rules of exponents and logarithms, I know that I can just take the n, it's equal to n natural log of e, and from this third line above, the natural log of e is equal to 1, so therefore n times the natural log of e is equal to n.